G'day, Richard Maher again from Mars Classes. Today I'm going to be discussing three ways of measuring the EMF induced in a generator. Now these three measurements sometimes cause confusion, so I'm hoping that this presentation will clarify some of that confusion. The three ways of measuring EMF are the average EMF, the RMS or the root mean square EMF, and the peak or maximum EMF. So when we look at a generator, it consists of a coil which is rotating in a magnetic field. Now I've represented it here as a rectangular coil, and I've got it currently perpendicular to the magnetic field. So you see the effective area which is being cut by the magnetic field is the whole area of the coil. So that's going to be the whole, the flux will be the whole area of the coil multiplied by the magnetic field strength. And then I've got two axes on the right hand side where the horizontal axis is representing that flux, that B times A. And at 0 the flux will be maximum. As we rotate it through a few degrees, we'll see that the effective area that the coil presents to the field is now less. So there's going to be a smaller amount of flux cutting through it until you get round to when it's parallel to the field, and there'll be 0 flux cutting through the coil. And I'll just keep rotating around and changing the effective area that it's presenting to the field as it rotates. Now, a lot of students have a bit of difficulty trying to explain why it is at certain locations you're going to get maximum EMF induced, and at some locations there'll be 0 EMF induced. Now, we know that the EMF induced is calculated by looking at the rate at which flux changes. So let's have a look at this graph that I've presented here. The curve represents the amount of flux. So if we're looking at the gradient of that curve, that will tell us what the rate of change of flux is. At 0 degrees, if I look at the gradient, the rate of change of flux is 0. So at that point there's going to be 0 EMF induced because there's no change in flux occurring at that time. At 90 degrees, the rate of change of flux is maximum. So at that point there, you're going to get the maximum EMF induced. And again, at 180 degrees, it's back to 0 rate of change of flux. Now, as I said, the EMF is the rate at which flux changes. So that's how we're going to calculate the value of the EMF. So let's have a look when it's at 90 degrees, when it's parallel to the field, when the EMF induced we're saying is maximum, and see if we can work out another way to determine what that maximum EMF is. So when it's parallel to the field, the side of the coil on the left is rotating down through the magnetic field, and the right is rotating up through the magnetic field, and both of them are cutting the field lines perpendicularly. So you're going to get the full induced current being produced in them. So the induced EMF in each of them is represented by those arrows there. Now, if we're going to calculate how much EMF is induced, in a previous video I looked at the fact that we can calculate the EMF induced in a wire moving in a magnetic field by multiplying the magnetic field strength by the length of the wire by its velocity. Now, in the generator though, there's not just one wire. Most generators have a number of loops of wire looping around, so there's n numbers of coils. And also, because the EMF is induced on each side, there's two lots of wires producing EMF. So the EMF total in this instance is going to be 2NBLV. And as we said, this is where this is occurring right here, right now. This is where the maximum EMF is induced. So we can reduce that equation to say the EMF maximum is negative 2NBLV, and that's when it's parallel to the magnetic field. That's going to be the maximum EMF induced. Now there are a few other equations we can use to calculate the maximum EMF because sometimes you won't have all of those values in that equation. So if we recognise that the velocity of this turning coil is turning through a circle, and the velocity is the displacement on time, we can say that the displacement is a circle, which is 2 pi r, and it'll do one revolution in one period. So it can replace velocity with 2 pi r on the period. And because the period is the inverse of the frequency, if you've got the period on the denominator, you can bring it up and write it as frequency on the numerator. Now if I rearrange the equation and just take the pi down to the front of the equation and then group together a few other terms, I've got negative 2 pi NB, and then I've grouped together L and 2R and multiplied by F. Now if this is a rectangular coil, L is the length of the coil and 2R will be the width of the coil, so we've got length times width, which is equivalent to area. So fantastic. We've got another equation here, how we can calculate the maximum EMF induced in this alternating current generator. But there's these other two types of EMF people talk about. They talk about the average EMF and they talk about the root mean square EMF. So let's consider what they might mean. So let's go back to our coil, and we'll have it rotating through from maximum flux going through the coil to zero flux going through the coil. Now that's the biggest change in flux that's occurring during the rotation, to go from maximum to minimum, and it does that maximum to minimum in 1/4 of a turn. So you're going from zero EMF to maximum EMF in 1/4 of a turn. So if we want to see what the average EMF is, we could just consider that 1/4 of a turn. And if we averaged out the between the maximum and zero, we could see that we know the EMF is the rate of change of flux, and if it's changing from maximum to zero and it's changing from maximum to zero in 1/4 of a turn, we can write it down as that. So therefore the average EMF is going to be the maximum flux, or BA, divided by 1/4 of a period. Okay, now when we do that, really when you look at an alternating current generator, it doesn't make too much sense, because when you're looking at the whole generator going over multiple cycles, you'll see that sometimes the EMF is on the positive side, sometimes it's the negative side. If you average all that out, it's going to get to zero, isn't it? So the only way that really makes sense is if we fully rectify the wave. And to do that, you'd put a commutator in your generator to give yourself a DC generator. So when we do that, we get a fully rectified wave. If I look at I've put in a dotted line to represent this average value and the maximum peak value, which we've shown how we can determine previously. If we look at the area of the curve between those two dotted lines, that red thing there, and we look at for all of the rectified peaks there, if we take that area and jam it into the gaps, it fits exactly, if we've got the average EMF in the right location. So what we now have is, with this fully rectified curve, we can see that if we average it out over time, there is one value for EMF we can use. Now I've reduced the equation there from the maximum EMF divided by 1/4 of a turn to 4 times the maximum EMF, AB, times the frequency, because frequency and period are inversely related, and 1/4 of the period will come up as 4 times the frequency. Now if we want to see how that average EMF relates to the maximum EMF, the mathematical relationship actually comes out to be that the maximum EMF is equivalent to pi on 2 times the average EMF. But as I said, the average EMF is not really that useful if we're looking at a fully alternating current, which is what you'll have in your home. So why is it that when we here in Australia we talk about our voltage at the home voltage being 240 volts, or in America they'll talk about it 110 volts? It can't be the same voltage all the time, the same EMF all the time. So there's got to be some effective value, and the effective value is what we call the root mean square. Now the root mean square comes out to be, if you look at the maximum EMF induced, if you divide that by root 2, that will give you what we call the root mean square. Now our peak voltage here in Australia is around about 340 volts, and I think in America it's around about 170. And if we divide them by root 2, we get 240 volts in Australia and about 110 in America. So again, going back the other way, if we look at if we are given the root mean square voltage, if you multiply that by 0.2, that will tell you what the peak voltage is, or the maximum voltage is. Okay, look, I'm hoping that those descriptions there clarified some misunderstandings you may have with calculating these different EMFs in your generators. I think I'll leave it at that for now, and until next time, I'll speak to you next time. See ya.